Today you will learn more about error identification and correction in remotely sensed images. In my last lecture, I have given you the brief introduction about error associated with remotely sensed images. In this slide, we will quickly go through the sources of such errors. So, as we all know that sun is our source of energy in case of passive remote sensing. So, here sun is illuminating the surface, right, and which gets reflected or emitted or back scattered from the surface and which reaches to our sensor, which is located in the space. So, this particular energy which is coming from the sun, it has to travel through the atmosphere to our surface and then it has to back travel to space through our atmosphere. Here first thing is source sensor geometry that we have already covered in the last lecture, that what do you mean by source sensor geometry and field of view, and what is the impact of these two on the remotely sensed images and what kind of error they can introduce to your data, right. In this case, we assume that our atmosphere is opaque, there is nothing to interact. So, everything is coming and going back to this particular sensor, right. But we have atmosphere where we have clouds and different atmospheric constituents, they introduce atmospheric error. And here you can see, because of this path radiance, additional information or the value is being recorded by the sensor, which is located in the space, right. This error is known to us. Now, there is a new error which is called radiometric error. So, this error is related to your instruments. So, errors introduced by your instrument. So, here instrument means our sensor. So, what kind of errors it can introduce, that we will see in the detail. Now, from all these measurements we have a image and DN number, and DN numbers are basically the radiant flux from this surface, right. Now, here we have another component called geometric error. So, geometric error is also part of this error associated with remotely sensed data. Now, material property also plays very significant role, and the last one is topographic error. So, topography, because of the undulating surface, what kind of error it can introduce to your remotely sensed data, right. Now, we will continue with atmospheric error. Atmospheric correction is a process by which the effects of atmosphere on the satellite or airborne images can be removed. So, here remember, when we are talking about atmospheric correction, so atmospheric correction or atmospheric error is always associated with your space based measurement as well as your airborne measurement. So, here you can see, this is one example, this is the raw data recorded by the sensor and this one is the corrected image. Atmosphere is composed of various stable and variable constituents. So, one of them is stable components, which includes gases like nitrogen, oxygen and several inert gases constituting of 99.9% of total air, and the other one is variable components, like here we have carbon dioxide, water vapor and solid liquid particles which contribute to this variable components and which vary with region, season and weather condition, right. The suspended liquid and solid particles are generated from volcanic eruption, sandstorms, forest fire, industry, transportation, construction, etc. So, here there are many components which are involved contributing these variable components to our atmosphere. These are called aerosols, which includes haze, smoke and fog. So, interaction between atmospheric component and electromagnetic energy. Here the most efficient absorber of the energy include ozone, carbon dioxide and water vapor. So, these three are the most efficient absorber, right? The absorption band in the electromagnetic spectrum is distributed as, so here what I mean to say, that for ozone, carbon dioxide and water vapors, what are the wavelengths which are sensitive? Sensitive means in which wavelength basically the signature of this ozone, carbon dioxide and water vapors are actually significantly visible in our recorded data, right. So, if you see here for ozone, here we have first range, that is 0.22 micrometer to 0.32 micrometer, then we have 0.6 micrometer, then we have 4.7 micrometer, 9.6 micrometer and 14 micrometer. So, if you have a satellite which is sensitive in these particular wavelength region, then you can easily find the signature or the presence of ozone in our atmosphere, because in these regions or in these wavelength regions, the ozone will give its own characteristic absorption feature or interaction signature, right. Now, the next one is carbon dioxide. So, here you have 1.4, 1.6, 2, 2.7, 4.3, 4.6, 5.2, 15 micrometer, right. In case of water vapor, you have all these wavelengths where this wavelength water vapor signature can be identified. So, as I told you in my first lecture, initially when we started remote sensing, then we considered all these wavelengths like a error. Like if your sensor is sensitive in all these wavelengths, you cannot really use those images for any qualitative or quantitative analysis. But nowadays, with the advancement in the technology, these wavelengths are actually useful for an atmospheric scientist. Correction of molecular absorption and scattering by the stable components are easy since they are not variable in space and time. So, here you can see the correction of molecular absorption and scattering by the stable components. So, it is not very difficult because all the components are known, all the absorption features are known. So, you can easily identify their concentration in the remotely sensed image and you can remove their effect. But the problem lies with the variable components, where you do not know what is the proportion of carbon dioxide or other gases which are emitted by the local industry or from the any other local sources. Atmospheric correction mainly involves estimating the influence of water vapor and aerosol. So, here the surface characteristics and the received energy are connected by the radiative transfer model, where this equation explains the relationship between surface characteristics and the received signal by our sensor, where L is your radiance, then we are also using observed angle coordinate, then relative azimuth between solars, then solar direction and the observation direction, where mu is cos theta and theta is the zenith angle, and aerosol optical thickness, single scattering albedo, scattering phase function. So, all these parameters are used to define the surface characteristics and its emitted signal or reflected signal which is sensed by our sensor. Aerosol are small suspended atmospheric particle. Their size ranges between 0.001 to 10 micrometers. So, it is very small. They significantly affect the global climate by changing the total radiation budget of Earth atmosphere system. And now we will see how this aerosol is going to affect our life as well as our remotely sensed images. And they can directly interfere the reflected or emitted signal by the process of absorption and scattering. So, the spatial variation of AOT, that is aerosol optical thickness, can be corrected on the basis of spectral, temporal, spatial, angular and polarization signature, which is measured from the remote sensing technique, right. So, effects of aerosol, what kind of effect it may cause or it is causing. So, first one is increased scattering and absorption in atmosphere. So, if you are working in shorter wavelength, working in shorter wavelength means if your sensor is sensitive in shorter wavelength, then you will have more problem from this scattering and absorption. Then it can also change the albedo of the surface. So, albedo is basically the broadband reflectance of the surface. So, broadband albedo is, if you see, this is your surface, this is the source, it is illuminating your surface and light is getting reflected. So, in case if you have more haze here, right, or aerosol, right. So, what will happen, this measurement when we refer albedo, albedo is a broadband reflectance and it also affects the lifetime of the cloud. Then indirect effect on snow, glacier by increasing the total radiation budget of earth atmosphere system. So, basically what happens, these aerosols can also trap the heat coming from the sun, which is, and they are not allowing that to again go back to the atmosphere. So, what is happening? This is ultimately changing the total radiation budget of earth atmosphere system, and change in weather condition, that is again a result of this presence of aerosol. Now, the spatial variation of aerosol optical thickness can be corrected or estimated on the basis of spectral, temporal, spatial, angular and polarization signature, that now we will see. So, let us start with spectral information based correction, where we have dark target method, and this method assumes some bands are affected by aerosol more significantly than other bands, and where the minimally affected bands, that means less affected bands, are used to determine the surface reflectance, and the aerosol optical thickness of the band sensitive to aerosol are then estimated from the surface reflectance. So, these are very simple statements, I hope you can understand easily. This is one of the most commonly used method for atmospheric correction for MODIS and MERIS data. So, here this is one type of sensor which is available, the data is available with us, and you can easily go to their website, register yourself and download these data sets, right. So, now next is spectral information based correction. So, here you have mid infrared dark target method. So, the apparent reflectance of a dark target in the mid infrared band is less affected by the atmosphere and thus approximated as surface reflectance, right. Based on the linear relationship between MIR, red and blue reflectance, the surface object reflectance in the blue and red band is calculated and the AOT in the red and blue band is estimated. So, now here you can estimate the AOT from this particular relationship. Now, next is near infrared dark target method, where this method is applied when MIR band is not available. So, you have to remember that different satellites have different configuration and they are capable of handling or measuring different bands in different wavelength region. So, it is not necessary that X sensor can give you 5 bands, so that Y can also give you 5 bands, no, and that too in a particular wavelength range, right. So, you have to check their technical specification. If you are checking for the X satellite and you are seeing that 0.4 to 0.5 is your first band, and then 0.5 to 0.6 is your second band, and 0.6 to 0.7 is your third band, right. So, this is the configuration of your X sensor, but if you see the Y sensor, so here I will change this to 3, right, and here let us also change this with 3. Now, this Y sensor can have first band in this and it may not record this one. So, depending upon their technical specification, the first band of Y sensor may be this one, which is the second band of X sensor, right. So, you have to check your data whether that data is having the MIR band or not. If you are having MIR band, then you can use the previous method. If you do not have, then you have to find the alternate solution. So, this is the alternate solution. So, this method is applied when MIR band is not available. This is based on the linear relationship between NIR reflectance and the rate band reflectance, which is used to calculate the atmospheric visibility of the rate band, right. Now, the next one is near infrared. So, the method assumes that the surface reflectance is constant in a certain time interval, thus only some value of the pixels are significantly affected by aerosol. The AOT is estimated from surface reflectance calculated from values that are less affected by aerosols. So, here you have linear regression method. So, a linear relationship is established between image of different time period based on the apparent reflectance of time invariant pixel, right. So, here this is very important. That means, pixels which are not going to change with time, does not matter what is your weather condition or what is the other parameters, right. So, you have to find those pixels which are not going to change with time. The accuracy of this method is better when the imagery is acquired in synchronization with the corresponding surface reflectance measurement. So, here what it means, when you are going to measure this images from satellite, the same time you have to take your ground instrument and go to the field, and the time when a satellite is going to pass that area, the same time you have to measure the reflectance value on the surface. So, then what will happen, that all the parameters remain same, and then you can correlate these two data sets. Considerable error occurs if only one type of pixel with little change in brightness exists in the imagery, right. So, here what does it mean? Only one type of pixel. So, one type of pixel means the whole area is homogeneous, only one type of material is present, then you may face some problem and the error will be more. So, next method is improved multi-temporal imaging method, where this method detects the observation of each pixel least affected by the atmosphere over time series images in a certain time interval, right. So, we are talking about the temporal images. Then the AOT of the hazy image is calculated using lookup table. So, lookup table is basically a table generated from your image which has all the parameters in tabular form. So, whatever calculation you are going to do or the linear relationship you are going to establish, that you will do it in the tabular form, not on the image. So, if you change any value here, that can be removed or added later on in your image. So, in this case your image, the raw data will be preserved. This algorithm produces better correction result for brighter target imagery. So, if you are having brighter target in your image, this a particular method works very well. Next is angular information based correction, where this method is mainly used for airborne and aerospace sensor that observe the earth's surface from various angles simultaneously. So, multi-angle data is used for atmospheric correction, since large observation angles are generally more sensitive to aerosol impacts. Why, we will understand. This method is advantageous since aerosol impacts are different for image acquired from various angles. Haze detection is difficult in the case of brighter surface target and shorter atmospheric path. And observation at large angle increases the intensity of the path radiance of haze, and this provide easy detection of haze in large angle observation, which is difficult to detect at nadir observation. Next is spatial information based correction. Here these correction methods are based on matching of the spatial characteristics between clear and hazy region. So, here for the same area, for the same scene, you will have two types of images. So, within image, two types of area. So, one is highly affected with this haze and one is very clear. So, you do not have any problem from the atmosphere, or I would say aerosol. So, the first method is histogram matching method. It is based on the assumption of the simultaneous existence of the clear area and hazy area caused by aerosol scattering in a single image, right. The surface reflectance of the clear area is determined by removing Rayleigh scattering, less aerosol scattering and gas absorption, right. The AOT is estimated by matching the histogram of the hazy region with clear region. Next is cluster matching method. In cluster matching method, basically it identifies the clusters or surface type using the longer wavelength information with least sensitivity to aerosol, right. So, what do you mean by this cluster? So, basically clusters are, you have a image and you have pixel values. So, basically you have matrix, right, and these matrix are having some numbers like x1, x2, x3, x4 you can write, and then based on their values you can group them into different clusters. So, that is what cluster means here. So, here clusters of the value derived from the images, right. So, next point is the histogram of these clusters are then matched over the study area. So, histogram, for any histogram, what is the x and y axis? So, x is your value. So, in this case it will be dn value, right, and y is always our frequency. So, from this matrix you will have to identify the unique values. So, let us say this is x series and then y series, then z series, right. So, here you have x, y and z. These are unique values from this particular matrix. So, what is the frequency of this x, y and z? So, I will give you some real example, like if you have 8-bit data where the range of the value is 0 to 255. So, you have to find out how many times this 2 dn number has occurred. So, instead of x I can write 2, and then it might have occurred maybe 1000 times depending upon the size of your image. Then y is here, z is here. So, like that you will have the histogram. So, if you see the histogram, ideally histogram always we represent in Gaussian form, right, where we say that all the values range starting from 0 to 255 in case of 8-bit data. This particular histogram has occupied the full range and all the values are equally distributed, right. But it does not happen in the natural case. So, what you will have? You may have two different types of peaks here. So, this is known as unimodal, this is known as bimodal. You may have 3, 4 or 5 or 10 peaks, right, depending upon the range of the value and the distribution of the values. So, here the histogram refers to this particular distribution of the DN values. Next point is, it is based on the assumption of the simultaneous existence of the clear area and a hazy area caused by aerosol scattering in a single image. This method can be applied for images with different landscape and small hazy patches. So, that means in the whole image you have small pockets where you have the effects of more aerosol or haze. Next one is polarization information based correction. So, here atmospheric scattering has a strong polarization in the visible band, while surface reflectance exhibit low polarization. So, that means if you are having a scattering effect in your data, you will have strong polarization in your data, whereas the surface reflectance from the surface or from the target, that represents or that has very low polarization. That means if you can identify the strong polarization and low polarization, then you can easily identify the effect of scattering in your data, and that is due to atmosphere. The aerosol optical properties can be better determined by the combined use of polarization and radiation information, right. The French Space Agency developed the running remote sensing polarization sensor POLDER, and it provides radiation, polarization and multi-angle information for aerosol retrieval, because nowadays aerosol is a very important parameter which atmospheric scientists are studying, because it is changing our climate. So, that is why now you can see there is a dedicated satellite which can give you information about radiation, polarization, multi-angle information for aerosol retrieval. It determines the aerosol optical property using the POLDER data is based on the comparison between the lookup table from the vector radiative transfer model and the actual observation, right. This is the spectra of gypsum, right. And here you can see there are many troughs. Trough means where you have depressions, and you have many peaks, right. So, it also depends whether your satellite is sensitive in that particular wavelength range where you are intended to identify some error or some information. So, for example, here this is in case of Landsat, you can find out that first band belongs to this particular area, second is this, third is this, fourth is this, fifth is this, seventh is this, right. And you can see there are many features which are not covered by this particular sensor. Why? Because that sensor does not have any band in this particular wavelength region. So, you can only study those information which are available in this particular bands. So, now here this 1.4 micrometer and 1.9 micrometer, that is coming because of the atmospheric water, right. So, you can see that during the designing of this particular sensor, people have taken care of this wavelength, and so that they did not put any band here, right? Why? Because that will be mostly affected by your atmospheric water. So, that means the objective of this particular sensor launch was something different, to study the surface behavior or surface characteristics. So, in case if a atmospheric scientist develop a sensor, then he will definitely put a band here and here, right. So, this is what I wanted to convey, that if you want to correct for the water vapor or for any error, and that is having a characteristic absorption feature, in case of water vapor it is here and here. So, you should have a sensitive band or sensor which is sensitive in that particular wavelength region. Then only you can try removing the effects of those components. So, the removal of water vapor effects is important in the quantitative application of the near infrared and mid infrared remote sensing imagery, right, that you have understood, because that is going to contribute more error in your measurement. So, a water vapor absorption channel is used to obtain the atmospheric column water vapor content. That means a water vapor absorption channel means, here I am talking about the bands, is used to obtain the atmospheric column water vapor content. So, what is the content of the atmospheric water vapor? That you can estimate using the wavelength bands, right. Many band ratio algorithms are being used for the column water vapor estimation, such as narrow band, wide band ratio and linear interpolated regression ratio methods. The impact of the atmospheric path radiation is not removed in the band ratio method, leading to a great ratio due to decrease in the surface reflectance, right. Then the band ratio algorithm are more suitable for region with high background reflectance. High background reflectance means, if you have a image and your target lies somewhere here, right, and basically that is having some low reflectance value compared to the surrounding, right. So, surrounding will have higher values and your target will have lower values, that you have to know before. Then this band ratio algorithms are suitable, right. Then the accuracy of water vapor estimation is reduced in the low reflectance region due to underestimation of water vapor content for darker surfaces. The APDA method removes the impact of atmospheric path radiance. This can be used to improve the accuracy of water vapor content estimation in the low background region. So, that was the high background region case, and now here we are talking about the low background region. So, your target is having high reflectance. So, the atmospheric correction methods can be grouped into two major categories. First one is relative atmospheric correction, where we have scene based and ground based. Next one is absolute atmospheric correction. So, relative atmospheric correction is basically where you are going to use some standards and you are going to correct the images. But in absolute atmospheric correction, you will have to know all the atmospheric constituent parameters and what is their values, and based on that you will model the atmosphere. So, there are various methods that can be used to achieve absolute and relative atmospheric correction, that we will see. So, first one is flat field method. A small homogeneous area of non-absorbing material need to be identified. What does it mean? The small homogeneous area. So, suppose you have a image, right, and you have a water body. So, in water body, this particular center pixels or the center area, right, the central area will have no effect of soils. This will contain pure water, right, does not matter what kind of water it is, but comparatively compared to this sides you have better values in the center pixel, right. But here we are not talking about only homogeneous area, we are talking about homogeneous area of non-absorbing materials. So, if your sensor is sensitive in all these bands 1, 2, 3, 4, 5, 6, then you need to identify which material does not have any absorption feature in all these bands, right. So, what you will do here? You will identify X material may be located here and then you will use it in the calculation, right. So, in this case I have drawn that one. The average value of the small homogeneous area is computed and then subsequently each pixel of the image will be divided by the calculated average value to produce a normalized image. So, what we assume, by averaging it with the calculated value, you are removing the atmospheric errors. In general, it is very difficult to define a homogeneous area which is having non-absorbing characteristic in the wavelength, right. So, if you are going to identify this blue band, so I will just go back to this particular. So, here in case you are going to correct this fourth band, then what you will do? This does not matter what material it is. So, you know that this particular material, it does not have any absorption feature here. So, it will be simply a straight line or close to a straight line. So, you do not have features like this in this, right. So, you can use this material location and the pixels and calculate the average value and then divide it with the whole image, right, but for that particular band only, because the same material cannot be used here, because here it has some absorption feature. So, you need to find another target which is having this kind of response in this particular band, right. So, that is why I have written here. In general, it is very difficult to define a homogeneous area within the area of interest. So, our area of interest in this case is from here to here, right. And what is the role of resolutions here? Like if you have low spectral resolution, if you have low spatial resolution, what effect it can cause? So, basically here when you have high spectral resolution, then what will happen? You will have better identification of the non-absorbing material, right. But in case of low spectral resolution, this whole wavelength will have maybe only 1, 2 and 3 bands, right. So, in this case it will be very difficult to identify a homogeneous non-absorbing material, but when you have more bands, then it will be easy, right. And when you have high spatial resolution, then what does it mean? Then you can correctly locate those pixels which are having those materials which are non-absorbing in nature in that particular band, right. And for example, clear water, deep shadow, exposed dark colored rocks are better if you can find out they are non-absorbing in behavior in your particular band, right. Next method is internal average relative reflectance, IARR, where we identify or we estimate the average reference spectrum which is used to calculate the relative reflectance spectrum for each pixel of the image. So, here what I mean to say, this whole image, right, will have one matrix. So, you can find one average value, right. Then here you will have one value, sorry, this will be 2, this will be 3, this will be 4. So, like that you will have spectra, one average spectra, right. So, here the ARS is calculated by averaging the whole image with respect to wavelength. That means, for that particular wavelength you will have only one value, that is the average value. So, each does not matter how many bands you have in your image. If it is 5 bands, you will have 5 average value, and that will be used to divide pixel wise. So, the first value of this average spectrum will be used to divide pixel wise here, right. Second will be used here to divide separately, right. For the relative reflectance image, each pixel of the input image is divided by the ARS. This method is useful when no calibration information is available and does not require previous knowledge of the study area. So, here in many cases what happens, we want to study some unknown places where we cannot go, then we are restricted to use such methods which does not require any previous knowledge or ground information, right. So, depending upon the spectral response along with the artifacts, real features may be suppressed or removed, because here we are going to use the average value calculated for this whole band, right. That one target which is having some DN value x1, which is similar to your calculated average value for that particular band. So, in that case, when you are dividing it, then what will happen? That feature will be removed from your image. So, this is the limitation of this particular method. Next one is empirical line calibration. So, here it forces the satellite data to match with the spectral reflectance data measured in the field. The in situ data is acquired at the same time and date of the satellite based measurement. So, here what we require is in situ measured data and at the same time and date. So, when your satellite is passing through your study area, the same time you have to be there and you have to measure the reflectance from your ground instruments. So, and then you can use this equation and you can correct your satellite images, and that we consider that will be free from your atmospheric components. Why? Because when you are going to measure it on the surface, you are going to less interact with the atmosphere. So, we assume that it is comparatively better and we are directly calculating the surface reflectance. So, here you can see this is the area where this particular sensor is active, and what we have to do, suppose if this is today 11:30 at on 13th 03, right. So, the same time you have to go to the field with your instrument and you have to measure the dark target and the white target, so that you can use it for the calibration. So, you will put a dark patch here and white patch here, and then you will measure the reflectance using such instruments, and then you will have these values like for dark target and for the bright target, and the same information is also available from satellite. So, what will happen here, you can easily plot these data sets. So, here you have dark target, here you have bright target, and in this side you have in situ data and this side you have satellite radiance data, and then you can definitely generate a equation and you can correct the whole image, right. I hope this is clear. This is very easy and very interesting, right. Now next is histogram adjustment method. So this method is based on the fact that infrared images are free from the atmospheric scattering effects, whereas the visible range are strongly influenced by scattering, and we assume that in longer wavelength region it is comparatively free from atmospheric scattering, right. And because of that fact we are using infrared here. So if you see a spectral response of water, so it will be like non-absorbing, or there will be no absorption feature in IR wavelength, right. So if you have any values in that one, that you can consider it is basically the contribution of atmosphere. So that is why this method is based on the fact that infrared images are free from the atmospheric scattering effect, whereas the visible images are strongly influenced by scattering, right. So minimum value of infrared band can be considered as the noise introduced by the atmospheric scattering. So if you have water body in your area, you can take that value like it is contributed from the atmospheric scattering. To remove the scattering effect, minimum value needs to be subtracted from each band. So what is the problem with the relative atmospheric correction? So with relative atmospheric correction method, it is difficult to relate satellite data with in situ measurement. Why? Because one, you are going to measure in the ground with less interaction with the atmosphere, whereas the other one you are measuring from the space where you have maximum interaction with our atmosphere and the local settings. So that means you cannot really correlate these two values unless until you do not remove the atmospheric effect from the satellite images, and this cannot be used to correlate the spectral signature measured at different geographic location and time. So I told you reflectance and emissivity, they are the unique value for a given material, right. So if you have measured it in IIT Guwahati campus or in your own campus, it should remain same. So if it is not same, that means the atmosphere or the other errors are present in your data, right. And it also significantly reduces the accuracy of the study, because ultimately what is the aim of all this remote sensing data generation and the analysis? Because we want to use it in some application. So when you are not going to remove, or your data is having the errors, then what will happen? Your result will also have that error. So because of this, we have absolute atmospheric correction, where this method are used to compute the surface reflectance from the recorded digital numbers. These surface reflectance values are unique and can be used to compare with the values measured anywhere else, right. So for this absolute atmospheric correction, we have radiative transfer based methods. So here we have Acorn, Adcore, Atrim and Flash. These are some of them. So we will see one by one what is their strength and demerits. Information required for absolute atmospheric corrections are fundamental atmospheric characteristics, because I told you this is absolute method where you have to model the complete atmosphere, right. So you need to know what is the fundamental atmospheric characteristic of that particular area. Then it also requires the information about spectral band which are sensitive to different atmospheric constituent. We have seen that image with different bands. Remember, geographic location, what is the location of your study area, latitude, longitude, date and exact time of data acquisition, satellite altitude, at what altitude your satellite has acquired that particular image, then mean elevation of the scene from sea. So, MSL. Atmospheric model to address the atmospheric scattering. Which model you are going to use? Radiometrically calibrated image radiance data. So, here our input data will be radiance data, not DN values. Wavelength information about each band with its FWHM, full width at half maximum, you remember. Then spatial resolution, what is the spatial resolution of your image. So, these are some of the important parameters listed here which is required in order to do absolute atmospheric correction for any given satellite images. So, first one is ACORN, and this atmospheric correction method is used commonly to calculate radiation within the wavelength of 350 to 2500 nanometer, that means 0.35 to 2.5 micrometer. Based on empirical method and methods based on radiative transfer theory, it can be used for atmospheric correction of multispectral as well as hyperspectral data, mostly used to calculate the effects of atmospheric gases as well as molecular and aerosol scattering. Atmospheric and topographic correction model, that is another model which is known as ATCOR, developed by DLR, that is the German Aerospace Center. Atmospheric correction method used commonly for processing bands in the range of again 400 to 2500 nanometer. In the previous method it was 350 to 2500 nanometer. Now, here it is 400 to 2500 nanometer. Mostly used for haze removal, correction of atmospheric impacts on the spectral reflectance of surface and removal of thin clouds, right. It can be applied for multispectral and hyperspectral data to both flat as well as undulating terrain. In continuation, ATCOR includes the sub-modules like ATCOR 2, ATCOR 3, ATCOR 4, and their applications are different. So, if you see ATCOR 2, it is used for flat terrain, considers 2 geometric degree of freedom of the flat plane, whereas ATCOR 3 is used for mountainous region, considers the terrain height with 3 degrees of freedom. ATCOR 4 consider 4 geometric degrees of freedom, includes scan angle effect along with x, y and z, right. Now, the next method is ATRIM, where it is developed by Center for the Study of Earth from Space, say CSES, University of Colorado Boulder. Atmospheric correction used commonly to calculate radiation within the wavelength range of 400 to 2500 nanometer. It determines the scaled surface reflectance from average and high-dose image. So, basically these two are hyperspectral images, and it is basically calculating the scaled surface reflectance. So, what do you mean by scaled surface reflectance? So, the reflectance value is a ratio and which is unitless, and value ranges between 0 to 1, but you can apply some multiplicative factor here and then your range can be 0 to 1000, right, or maybe 10,000 depending upon your multiplicative factor. So, you do not have to worry about the result, like when you see high values of reflectance which is more than 1, Basically, it gives you scaled surface reflectance, and it can also be used for other sensors with considerable modification in the code, right. It assumes the surface to be horizontal and Lambertian. So, these are the assumption, and it computes atmospheric transmittance of gases and molecular and aerosol scattering, used an approximate atmospheric radiative transfer modeling technique, and if topography is known, then the scale surface reflectance can be converted into real surface reflectance using this model. So, this is very simple, like you can understand easily. So, just go through it, and because it will take time for you to understand. So, first you have to clear your basics, fundamentals, and then slowly you can get it into the problems. The next method is flash. So, this is one of the popular method nowadays, which is used to correct the atmospheric effects in hyperspectral data, and it is also based on radiative transfer theory and reflectance ratio based method for visibility retrieval. It considers updated Morton based radiative transfer model for simulating radiation transfer property. It also includes a correction for pixel mixing due to scattering of reflected radiance from surrounding into the pixel. So, this is known as adjacency effect, because when a surface is getting illuminated from the source and this is getting scanned by your one detector, let us say this is one detector, and the next detector is basically sensing the next pixel on the ground. So, what will happen? There is a possibility of getting this signal mixed with this and this with this, right. So, that effect is known as adjacency effect, and which can be taken care by this flash algorithm, and it can be used for rapid atmospheric correction analysis of common multispectral, hyperspectral and aerial imagery, but with slight modification you can apply it in any multispectral and hyperspectral imagery. It is mostly used to correct water vapor, oxygen, carbon dioxide, methane and ozone in the atmosphere, as well as molecular and aerosol scattering. The result of from flash shows significant result under moist and hazy condition compared to dry and clear atmosphere. It can also be used to generate classified image of cirrus and other thin clouds for spectral smoothing. And the next method is Mortran. So, it is developed by Spectral Science Inc. and the Air Force Research Laboratory AFRL, that is from US, and it is used to calculate atmospheric transmittance and the radiative transfer algorithm for frequencies from 0 to 200 nanometer at moderate spectral resolution of 0.001 micrometer, and that you can say this is wave number. So, wave number is 1. It can also be used to estimate atmospheric background radiation, upward or downward radiation, radiance of single solar or lunar scattering, direct solar irradiance, etc. It computes line of sight atmospheric spectral transmittance and radiances over the ultraviolet through long wavelength infrared spectral regime, right. Remember, in the last class we have seen some DN to radiance, radiance to reflectance conversion. So, here there are some solved examples, because you need to understand how these methods works. So, for band 4 of Landsat 7 ETM plus data, these are the values, and you can easily calculate the radiance using this particular formula, and this is the value, right. In the next case, where we have to calculate calibrated radiance, and if you use this particular formula, then your value will be this, right. So, if you see the previous one, 197.46 and here 197.57. So there is a slight change in the value when you use dn2 radians normal equation and when you use this calibrated radians equation. So that means there is a change. So you need to take care of this L max, L mean, Q cal max, Q cal mean. So it is important and it is advisable to go for this calibrated radians equation when you are converting your dn to radians. And when the same data is used to calculate reflectance, so here this is RTOA, that means reflectance top of the atmosphere. So when you are using this particular value 197.46 and this equation, this is the reflectance value, and we all know that reflectance ranges between 0 to 1. So it should not be more than 1 and less than 0. So then your result is correct, right? So this is the ultimately your reflectance value calculated from Landsat 7 ETM plus data from dn to reflectance complete, right? Okay, thank you. That's all for today.